Hi everybody, in this video, let's move away from the ideal gas law and instead look at something else about gases. Let's try to find a relationship between the speed of a molecule and the mass of the molecule. So we will do this with the famous equation for kinetic energy, K equals 1/2 mv squared. So let me write that. And this equation will help us derive the relationship between the mass and velocity of particles. So we can think of K as energy, so in other words, as the temperature, since temperature is a measure of the average kinetic energy of particles. We can think of M in terms of molar mass, and we can think of the velocity as, well, just the velocity, or even a concept called an effusion rate. And effusion is the rate at which gas molecules flow through a pinhole. So you will see this very commonly in chemistry, but let's now derive the relationship between molar mass and the velocity of the particles, or the effusion rate, given that the temperature is constant. So if the temperature is constant, that means our K will be constant. So let's write two separate equations. Let's say that we have gas A with a certain molar mass and a certain velocity. Well, let's use not velocity, but rate, as in effusion rate, and this will be the effusion rate for A. And gas B will have a molar mass of B and an effusion rate of B. So let's relate the two. This is just like how we related volume and pressure and all sorts of stuff using the ideal gas law, but this time we're using K equals 1/2 mv squared. So let's use the next slide to help us derive this. K, well actually we said K was T, so T is kept constant, remember that. T is equal to 1/2 times the molar mass of A times the RA squared. And this is just replacing K with T, M with molar mass, and V with the fusion rate R. So now that we have this, let's write the second equation. T is equal to 1/2 molar mass B times the fusion rate of B squared. So seeing this, we can see that the T is equal to all this, so we can technically substitute this in here. So we get 1/2 of this, and I'm not going to say it because it's kind of repetitive, is equal to 1/2 of this. And notice how the 1/2s cancel out, because you can divide 1/2 on both sides. So let me just erase that, and we get this relationship. Let's go one step further, and let's actually move the variables around to the positions that I want them to be in. So if I divide both sides by the effusion rate of A squared, well actually I want to divide by the fusion rate of B squared times the molar mass of A, and you'll see what happens when I do this. On the left hand side, the molar mass of A will cancel out, leaving RA squared over RB squared, and this is equal to, on the right hand side, the RB squareds cancel out, leaving the molar mass of B over the molar mass of A. And we can go even one step further and square root both sides and say that the fusion rate of A over the fusion rate of B is equal to the square root of the molar mass of B over the molar mass of A. So deriving this, we figured out the relationship between the fusion rate of two gases and their respective molar masses. So this is known as Graham's law, and feel free to memorize it because it's a nice equation to memorize. or you could simply derive it from 1/2 mv squared, just in case you forget. So that's Graham's law. And let's try an example in order to see this relationship in play. So let's try to find the ratio between the fusion rates for neon gas and mercury gas. And let me tell you the molar masses of each of them. So these are the molar masses, and let's label these gases. So let's label neon gas as gas A and mercury gas as gas B. So using the handy equation, we can say that Ra over Rb is equal to the square root of the molar mass of B, which is 200.59, over the molar mass of gas A, which is 20.18. And typing this into a calculator, 200.59 divided by 20.18, and squaring that all, we get 3.153. So the ratio between the effusion rate for gas A and gas B is 3.153. Or in other words, neon gas travels 3.153 times as fast as mercury gas, or you could say that neon gas effuses 3.153 times as quickly as mercury gas at a constant T. So let's remember that all of this is at a constant temperature. Now let's talk about the Maxwell-Boltzmann distribution. These types of graphs describe the probability density, also known as the frequency, of a gas having a certain speed. So for example, this purple line showing, I think, xenon, is saying that most of the gas particles of xenon have a velocity that is over here, which is around like 250. So this is telling us that the velocity of 250 is very frequent for a molecule like xenon at a constant temperature. Or to put simply, a Maxwell-Boltzmann distribution shows the relative abundance of gases at certain speeds. So as you can see, for gases with a small molar mass, such as helium, you can see that the speed of these helium molecules are quite spread out and varied. And because they spread out over a large range of speeds, this causes a flat curve since there's a larger variety, so the molecules are not all clumped up to one speed, and they can be many different speeds. So that's why the abundances are not very high for each speed, since there's a wider variety of speeds to make up for that. Now, you can also see that the average speed for helium molecules at this temperature is around 1,100 something, and the average speed can be found by looking at where the peak is, and that's where you tend to find the average speed for molecules like helium. So as you can see, the average speed for molecules with small molar masses, it's actually quite high, and it's toward the right. Now, what happens if you increase the molar mass? Well, as we saw with the last problem, increasing molar mass makes the molecules slower, and this is reflected in the graph for xenon. As you can see, the curve is quite toward the left, which means that the average speed for xenon molecules is quite low at around 250 meters per second. And because the variety of speeds for xenon is quite low, a large percentage of these xenon molecules will have these speeds, and that is why the peak is so high, since the molecules can't really choose many speeds to have, so most of them just choose to clump up here. Now, why does helium have such a variety of speeds? Well, helium is easier to move since it has a smaller molar mass, so it has more choices when it comes to speed, since it can reach up to a maximum of about 2,500, while for something like xenon, it has a maximum velocity of, around like 600, and after that, it just flatlines. So that's what the Maxwell-Boltzmann distribution shows, and in the next video we will be doing something similar to this, but we will be comparing temperature and effusion rates in the next video. So for now, this is all, and have a wonderful day.